Good morning, good afternoon, good evening, wherever you're at. I hope you're having a wonderful day. We're going to finish up section 11.2 here by talking more about chords and arcs. Now, I just want to go ahead and prove these first three theorems, and then we'll talk about the application of those theorems there down below. And so to get things going here, I want you to actually fill in the whole theorem, theorem 11.6, and then we're going to talk about why it's true. So theorem 11.6 actually says this: in a circle, a diameter, so you can fill in that first blank there, a diameter that is perpendicular, okay, so that second blank is perpendicular, to a chord, bisects the chord and its arc, okay, or its arcs, okay. So as we look at this, a diameter, I'm going to go ahead and draw a circle here on my paper. Maybe I'll do it off to the side over here. Draw a circle, and I'll try to pinpoint a center spot, and I'll put in a diameter, okay? And then if I go ahead and draw a chord, okay, I'm going to go ahead and say that this diameter is perpendicular to this chord. Now, what is that doing to the chord? Well, it should be cutting this chord in half, but it should also be cutting this arc in half. And so, as we look at this, let's go ahead and label these points right here, and then we'll go from there. Now, what I hope that you see, or that we can look at, is almost everything in geometry comes back to triangles, especially when we're trying to prove things. And so, as I look up there, I hope that you can see that we have the reflexive property. Okay, EB is congruent to ED by the reflexive property. And we also have radii that are congruent to each other. Okay, and so in the end, we do have congruent triangles. Now, if I label these triangles, AEB is congruent to triangle CEB. It'll be by hypotenuse leg, okay? Remember the ways to prove triangles congruent: side, 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 angle, angle, side, angle, 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 side, and hypotenuse leg, okay? Now, because of the triangles being congruent, we would then know that AB is congruent to, I'll say BC or CB, it doesn't matter, by CPCTC, okay? And I think the other day we reviewed that concept. CPCTC stands for corresponding parts of congruent triangles are congruent. So now you can go ahead and mark out those parts as being congruent. I'll do it with a different color here to know that it was after we proved the triangles congruent. Okay. Now the other parts that would also be congruent within those two triangles would also be your angles here. So if I go ahead and jot down that angle, let's do AEB would be congruent to angle CEB. Again, this would be by CPCTC. Now, how does that help me finish off this proof here? Well, remember the second part of the proof right here was that the arcs are going to be bisected as well. And so this arc right here is bisected, and so those lengths right, or that measure right there and that measure right there would have to be the same. Again, remember, the central angles have to be equal to the arc measures, and so there's that direct relationship here between the angle and the arc, the angle and the arc. Okay. Now, what's interesting, and I oftentimes don't talk about this in class because we have to keep moving, but if those two arcs are the same, what do we know about this arc and this arc here? Well, they're also going to be the same, okay? Because, you know, this arc plus this arc equals 180, and this arc plus this arc equals 180, so therefore these two arcs would have to be the same, right? Okay? So again, I hope that really makes sense to you as we work out the little mini proof there, not wanting to forget how to prove things. For theorem 11.7, the next theorem, I'd like you to fill it out. It says this: in a circle, a diameter that bisects, so that first term is going to be bisects a chord that is not a diameter. Now, if I were you, I would put a little box around this, and we will talk about this again in a little bit because that's a key concept to this theorem here. Excuse me, is perpendicular to the chord. Okay, and so if we take a look here, you've got a circle, and I want to put a diameter up here in my circle, so here will be my diameter. And if it bisects a chord, so I'll just go ahead and say that this chord is being bisected there, then there's a couple of things that are going to be true because of this. Okay, so if I label this A, B, C, and D, okay, and throw in the radii, what we know to be true is going to be this. Well, dB is congruent to dB by the reflexive property. DC and AD are congruent because they're both radii within the circle. And now we look at those triangles, and we look and see that the triangle ADB will be congruent to triangle CDB by what reason? Should be side, side, side. Okay, I hope you can see that there. Now that the triangles are congruent, you know that this angle right here and this angle right here have to be the same measure by CP, CTC. Okay? Well, if they're congruent to each other and their sum is 180, then what would their individual measures have to be? Well, they'd have to be 90, which is why we say it's perpendicular to the chord. Okay? Now, the question that I do want to consider with you guys is this part: why can't this be another diameter? Okay, it says that it cannot be another diameter, and that's because of this. If I were to draw another circle out, okay, and put a diameter down, we know that this center point divides that diameter equally, so we've got 2 equal radii there. Okay, and if I go ahead and draw just a random other diameter in, okay, like this, that center point is still dividing that other diameter equally. Okay, so basically, if this read in a circle a diameter that bisects the chord is then perpendicular to the chord, well, obviously this is a chord, so is this one. They're bisecting each other, but I can tell you right now that angle is not 90 degrees. Okay, there's only one special situation that a diameter is going to be perpendicular to this diameter, and that's if it's completely, straight up and down. Okay, but as we talked the other day, there's an infinite number of radii, an infinite number of diameters within a circle, and so as a result, your chances of getting that are very slim. Okay, and so that's why we say just to stay away from that. That is not a diameter. Okay. All right, the last one, theorem 11.8. says this right here: in a circle, the perpendicular bisector of a chord, okay, so those 2 blanks, perpendicular bisector of a chord, contains the center of the circle. All right, so if I were to go ahead and draw another circle over here, okay, and I'm just going to go ahead and draw just a random chord right here, okay. Now I'm going to locate the center of that chord. Okay, I'm just going to guess on where that's at, but I'm going to say it's right there. And so I'm going to go ahead and draw a line perpendicular from that point. So if I go ahead and do this right here, okay, forms a right angle, perpendicular. Okay. So according to the theorem, somewhere along this line should lie the center of the circle. Okay. And so if I go into A, B, C, and let's say that we have D out here, okay, that, I'm going to say if it's the center, the distance from A to D and the distance from C to D would have to be the same, okay? And so as a result, if we can prove that A to D and C to D are the same, we know that we found the radius, the center of the circle, okay? So what else could I use to prove the triangle's congruent? Well, if I go ahead and mark the reflexive property here, we know we've got congruent triangles. By what reason? Hopefully you're thinking side angle side. We've got those right angles and then the two sides congruent, okay? So we've got side angle side. Now, from there, I then would know that AD is congruent to CD by CP, okay? All right, so here's the deal. You may be thinking that this point could be anywhere along here, and it would still be equidistant from A as it would from C. And you're exactly right. Okay. The problem is this: if this is not the center point, okay, then as it moves away from this chord in one direction or the other, okay, we get further from A than we do C, or the opposite. And so the center point has to lie somewhere on that other chord, this chord right here. Okay? All right, so with that being said, let's take a look at some examples where we apply this. And I really don't think that these are going to be very difficult examples. There may be a couple of tricks, and I'll try to point those out. But for the most part, I think that you guys are going to possibly go about doing these even faster than I could. So looking at the problem here, here's what I want you to see. If I was to extend this all the way out, okay, that diameter is perpendicular to this chord. So what does it do to that chord? Well, it bisects the chord. So we know that this and this are equal. So if that is 4 right there, how do we find x? Well, I hope you're thinking the Pythagorean theorem. Again, on these type of problems, as the pictures get busier and busier, don't be ashamed to go ahead and draw out the pictures. Okay? And so we can just jot this down. And we can go ahead and solve for x. Okay? So, if I go ahead and finish up, subtracting 16 from 25, and then we square root that. What's the square root of 9? 3. Now, some of you may have already had that down because that is a triple. Okay? It's a 3, 4, 5 right triangle. So, if you did, kudos to you. You were able to get it a lot faster than by working it all out. Okay. Number 2. If we look at number 2, here's the key to this problem. Notice that this 3 is a radius here. So if I go ahead and rotate that radius down to that point right there, okay, I'm actually going to get rid of all the work up here so you can see a little better. This length here is a length of 3. Okay. And so what we have as of right now, if I redraw this triangle outside here, got the right angle there, you've got 2, you've got 3, and I'm going to label this as y. Okay? And if we can solve for y, we've got a diameter that is perpendicular to the chord. So again, remember, it bisects this chord. It cuts that chord in half. And so as a result, if I can find y, which again is this portion of the chord, then I can double it to get the entire length of x. Okay? So if we work this out, 2 squared plus y squared is equal to 3 squared. Okay? We then subtract 4 from 9. And then we square root 5. Now, the factors of 5 are just 5 and 1. It's prime. Okay? So we can leave it like that. Now, x is twice the length of y. So if I plug in the y right here, there's my value of x. Okay? All right. Now, for number 3, I want to figure out what this length is right here. You can do it in one of two ways, actually. All right, sorry about that. I got a student that came in real quick. Anyways, so we're back to solving for x right here. In order to figure out what x is going to be, I'm actually going to go ahead and draw a line perpendicular, diameter perpendicular to this chord length right there. Now I'm doing that on purpose because remember, not only does this diameter bisect this chord, but it also bisects this arc right here. Okay. Now how does that help me out? Well, if this arc is 120, then this arc right here is half as much. That's 60 degrees. Now remember what we said, it's even written at the top of the board here, that the central angle measure is equal to the arc measure. And so if I go ahead and put this in right here, this is 60 degrees, okay? And if I, again, the picture is kind of getting kind of busy over there. So I would go ahead and draw it outside the framework of the problem. We have a 60-degree angle right here. And then you have 12. And then I'm going to put y. Okay, now if I find y, I can double it to get x, right? Okay. So you can do one of two things. You can either use your 30, 60, 90 triangle rules, or you can use your trig functions. Now, it's going to be a lot easier to use your 30, 60, 90 triangle rules, but if you don't remember them, I totally understand. I mean, they're easily forgotten, but let me just reiterate how to find that. If this is the 30-degree angle, 60, this is x, 2x, and x radical 3, okay? And so as I look over here, here's the 30, so here's x, here's 2x, and here's x radical 3. Well, if you remember when we did these, if I solve for x, dividing by 2, I get 6. So this length is 6, and so y is actually 6 radical 3. Just plugging the x in for x in right there, okay? So as a result, to get x, the x here, not the x here, because we needed that to get this one, all right? To get the x here, I'm going to double y. So if I double this length here, I get 12 radical 3. Okay? So if you understood all of that, that's awesome. And you could definitely do everything that way. You could also use trig functions, which I believe more of you are more comfortable with. And so I'm going to take a moment and show you how to use the trig functions here. There we go. All right, so to use the trig function to find y, here's your opposite side, and here's your hypotenuse. So as a result, I'm going to go ahead and do, let's see here, this would be the sine of 60 is opposite over hypotenuse. Okay? Now, if I go ahead and cross multiply to solve for y, cross multiply, you get that right there, okay? And you can plug that in if you want, you don't have to. We just know that x is going to be twice that much. So if I go ahead and do this, I wrote that wrong, x is twice 12 times the sine of 60, okay? You can get the value of what that is. And so if I plug this in, 2 times 12 times the sine of 60, okay, you end up with 20.8, okay? And you could always double check your work if you weren't sure about the 12 radical 3, because I'm pretty sure if you type in 12 radical 3, let's see here, 12 radical 3 gives you 20.8, so we know we've done it correctly, okay? All right, so on to the last problem, okay? So those first three, we're just understanding that the chord being perpendicular to the diameter being perpendicular to the chord bisects the chord and its arcs, okay? So this one, you got to get a little bit creative on, and there's lots of different ways that you can do this, but one thing that you could do is either say, okay, this is 86, so this is 86, or you can go ahead and take 180 minus the 86 and get what's left over here, okay? And so if I go ahead and do that, 180 minus 86 gives me 94, and so this arc over here is 94 degrees, okay? Now, what I'm going to do to get x, all the problems that we've worked with so far come back to right triangles. Well, the same thing is going to be true here. I'm going to go back to a right triangle. I'm going to make this a right triangle. Now, that's helpful because this length is 10 and this length is 10 because I bisected that chord. So if I put that down, that this is a length of 10, okay? But I've also bisected, I'll go and do this, there you go. I've also bisected this, this arc here, okay? And so as a result, this angle right here is half of 94, 47 degrees, okay? Now how does that help me out? Well, let me draw this whole picture, this whole right triangle separate from everything so you can see what's going on. If I do that, here's what we have. Right angle, 10, 47 degrees, x. Okay? Now I would hope that you'd be looking at it and be thinking, oh yeah, that's an easy problem. Okay? We've done a lot of these before. And so as you look at it, you can use your trig function, sine in this case because it's opposite. And this is the hypotenuse. All right. So from there, the sine of 47 equals the opposite over hypotenuse. Okay. Now, if I go ahead and cross multiply, that equals 10. This equals x times the sine of 47. All right. We can go ahead and solve for x. Now, this x I can get by myself because this is multiplication. I'm going to undo that multiplication with division. So if I divide both sides by the sine of 47, we get what x is. Okay? And so in the end, x is going to be approximately 13.7. Okay? So, and I hope you're seeing this, that we're trying to turn these into right triangles. We turn them into right triangles, everything becomes a lot more simple. So, let's finish this up. Let's finish up the last two. And looking at the last two, we want to find the measure of arc AB. Now, the radius and the measure of arc AB. Okay? Now, the measure is going to be in degrees. So I want to make sure we've got that down. The measure is always in degrees. So in order to find, let's start with the radius. I can go either to A or to B. It doesn't matter. Now, remember that this diameter right here bisects this chord and the arcs. Okay? And so I can go ahead and break this up. This would be 12. And that would be 12. Okay? Now, in order to find the radius, I hope that you can see, if not, I'll go ahead and draw it out here. To find the radius, all we're going to do is go ahead and use your Pythagorean theorem. Okay, so very simple there. So if I do that, I have 5 squared plus 12 squared is equal to c squared. Okay? If I go ahead and square that, 25 plus 144 equals c squared. This would be 169. And the square root of 169 is a nice fat 13. Okay? So what we have there again is a Pythagorean triple. It's a 5, 12, 13 triangle. Okay? Now, the next thing that I want you to see is how do we find the measure of this whole arc over here, the degree of this whole arc, okay? In order to get that, I'm first going to solve for this angle right here. This angle right here, the same angles here. If I can solve for this angle, I know the measure of this arc. And if I know the measure of this arc, I double it to get the entire arc measure. Okay? So, how do I solve for this one? Well, remember, this is your opposite side, and this is your adjacent side. So as a result, I would probably use the tangent function. The tangent of x is equal to the opposite over the adjacent. Okay? Now, if we go ahead and solve for x, remember we use that inverse trig function there. Okay? And we can get what x is. Now, if I were you, I would hold off from getting x. Okay? I would actually go ahead and double it at this time to get your actual arc measure. So if we do that, let's see here, twice the inverse tangent of 12 divided by 5. Okay. And that'll be, let me write that down. The measure of arc AB measure is going to be equal to twice what we have here. Okay, and what is that going to be? It's going to be 134.8 degrees. Okay, all right, and that looks fairly accurate right there. It's not 180, it's close, you know, it's getting up there, but it's definitely not a 90 degrees, it's more than that. So I hope that made sense. To finish things up with this worksheet here, I'm going to let you go ahead and fill out number 2 because it's very similar to the first one, and then show me the work there for your credit for the lesson, and then we've got some practice problems for the next day in class. So you've been a great audience, and I hope you have a great night. Good night.